Okay, so we can use those last two relationships about these two, these two measurable properties of a fluid to get this, which is actually the bulk. Okay, bulk modulus elasticity E, used in strength of materials as well. But this relates now for all phases of matter, actually, because you get this expression here. So for a liquid or solid, right, this value is extremely small, right? Changing the pressure and the temperatures on liquids or solids doesn't quite actually change their temperatures that much. If you increase the pressure, if you increase, it's not too sensitive to this, but gases it is. That's where this is the difference. So for a liquid or solid, right, it's just the inverse of the coefficient of compressibility. So this is something that we just use for solids all the time, right? This inverse relationship of compressibility. But for a gas, this is where you change. So this expression right here is cool and important just because it's true, right? Based on some measure of this value, it can tell you, right, what they are. So for a gas, right, sort of much more greater than one, just it's not a negligible quantity is the thing. The idea is like if you do change the pressure on a gas, it's pretty sensitive temperature-wise, right? You can see that if you change the pressure on like a laptop, right? The laptop gun where I'm lowering pressure so you can just feel the temperatures change. Not exactly the same thing for water. Even if you're running water extremely fast through a hose or something like that, it doesn't feel like it got like a lot colder, right? So that's just how this number can show you where the bulk wants, where this is changed, right? The fact that it's just that for a solid and liquid, the modulus of elasticity is really just 1 over K, where K is a measure of compressibility. But for gases, it's like that, but there's another little term involved. And we'll use this once. But we'll use this when it comes to actual the speed of sound. But this is a neat expression just because you can rationalize solids, liquids, and gases based on this. And you can just ask yourself, well, if I change pressure, how's the temperature change? And then you have the betas and Ks. Again, those thermodynamic quantities, you can look at the expression, you can just make little changes in your head and ask yourself, does it change that much? It'll tell you if that term's small or not. You can also measure it too. Okay. Other thing about processes. So I guess another thing is that compressibility is also related to the process itself, just from what we've seen on these, right? These values as well. You know, the temperature can change based on the process. The P can change the process. These values can change. So even K itself, what was our expression for K? It was a change of volume and pressure. Those things, right? Those things themselves are process dependent. So compressibility is not just inherent to gases; it's process dependent. But just like before, I said how compressibility could be like extremely high temperatures, etc. You're not normally going to see that. So we can just think of it as compressibility is for a flow. Okay, maybe you've all noticed that I have never invoked the ideal gas law yet for all these total derivative expressions, etc. like that. But at this point, it's time that we start doing that. So, right, remember that here's how we're writing our equation of state. Okay, so this is the equation of state we're going to use. It's the ideal gas law, all right? So now we're going to use this in the thermodynamic equations to get like more workable equations, right? So we'll use that entropy version, right? This is a nice form because, right? It's all internal system properties, not process properties. That doesn't mean anything to you yet. Okay, so here's relationship. You divide by 1 over dV. If you're dividing by the change in volume, that would mean that the pressure had to be constant to do this. So all things held constant. So if I'm doing this, right, there's just the reason that if you did do that, you now have to say partial S, partial volume, partial U, partial volume. plus a pressure. So by doing this division by a differential volume, that would infer that these variables have to be held at constants, right? Where this would infer that these have to be constant pressures and temperatures. Okay, so actually from here, it can be shown what? It can be shown actually that the internal energy is only a function of temperature. It's not a function of, right? Boom. So using this, in Maxwell's relations, you can actually show that the internal energy is only a function of temperature. It's not a function of the volume in reality for an ideal gas. Same thing with the enthalpy. So that is what you got from using this. Ideal gases, plugged it into the entry version of the first law, wrote it this way, used some relationships I said before. I don't want to do this actually, because I think it's on the final. Okay, and then you write out that U has to be a function of temperature, not of volume. Same for enthalpy, just by algebraic manipulation, rearranging algebra definitions. Okay, that's really important because functions of one variable are really easy to Taylor expand, right? So that means I have a U naught, and then I have this, and then I have a T. Same with enthalpy. Some initial enthalpy, change, enthalpy, temperature, right? You could go further on too, right? And this is really just the definition of Taylor expansions, right? But something that we'll do all the time for this thermo stuff is that two differential terms squared are nothing. So you neglect these, right? If you get small enough, right, the differential terms, this is just so enormously small, smaller or less than this, with the assumption that this is bounded. But it usually is for continuous smooth functions, so it's okay. But that's something that we have to do a lot through all of this compressible stuff. It's the fact that two differential terms, it doesn't even have to be dt, it could be dt, a dv, that's essentially zero. Okay? So, not quite done yet. So sort of don't forget about those next two terms, right? Just leave it like this. So it's only a function of temperature, the internal energy and the enthalpy. So term, and then you have this differential term right here. So that is where you get these specific heat variables or specific heat quantities, right? You say these things are constant values or approximately. Right? You say that from experiment, I measured internal energies or some voltage. You got that these are basically constant. Okay, so what does that mean? These are those classic things you see all the time, the CV in your tables, right? What they are is they're a measure of internal energy, where V is held constant. That's where CV, the subscript V, means that this change in internal energy with respect to temperature, where I kept the V constant, and then H, CP. And then I had a CP, where this, okay, this is with constant pressures. So that is the definition now of these specific heat variables, right? They come from thermodynamics quantities. We use ideal gases. We expanded by Taylor expansion because the temperature was the only variable of that function. You did some experiments. You said that this is just the slope of a gosh darn line. You go like, well, then it's a CV, it's a CP. That's how you get these CVs and CPs. Okay, so after you get that, that's a CV, CP. You can do this with all properties, right? Because it's still measurable. I mean, these are ways to measure things, right? Differential terms are just, you just look at them and go like, got an experiment right there, right? You change, you look for slopes or maybe pointwise slopes, right? Okay, so then you do a little more. So here's CV minus CP. That ends up equaling R, right? And this is the same idea where this is the P, right? All true for an ideal gas. For an ideal gas law, you get constants approximately, but also you get that the difference is just a constant value. And that comes from the definitions of these things. You just plug these things and then use enthalpy expressions, etc. Very sorry. H. H, not U. CP. Subscript refers to what's held constant during the experiment, and then you just have to remember that the V return that this turns the volume, and then the P turns the enthalpy. Okay. Interesting question of how you actually measure enthalpy, though. Pretty cool. All right. So that's cool and all, but kind of another really important quantity is a gamma term. It's really helpful in analysis because it's just a ratio of the two things, right? Is the ratio of those two constant values. That's gamma. I think K sometimes as well. I like gamma because I find more books that use gamma instead of K, but I think in the book it's different. So, right, maybe some values for these sort of gas-dependent properties, right? That's the point, right? You did some thermodynamic analysis of functions and total derivatives to like pin down some property values that if you did an experiment that would be inherent to the property, not the process. So for air, you get these values. I think CV have 7, 1. I hate numbers. So this is kilojoules per kilo G. Okay, and then for the CP, it's like 1.0, some stupid number. And KJ and K. Okay, so these are just some values. And then a number I do like, because it's non-dimensional, right, is this. That gamma is just about 1.4. So you can remember that if you're working with air, dry air, or other things, it's about there, 1.4. So for all these expressions that we have coming up on state to state, right, they have expressions in terms of gammas and now Mach number as well. But the idea is that the gamma is just a number, so you plug it in there and you get the value, right? And depending on any gas you have, it could be helium, etc. You look up a table, you get these two values, you take the ratios, and sometimes they even give you the ratio a lot of times for the gas you're working with, right? You have nitrogen, right? Some mixture of gas. You can actually figure this out, and the table will just say, and gamma is this. So look it up, plug it into these power relationships. It's not that bad. What's important, though, is that this number relates to air, and it's not dependent on the process you did. It's dependent on the actual gas itself. So, and that is, we know that to be true because of the laws of thermodynamics, because that's how I derive what these things are. Okay, so one extra thing. So that is the gamma. Now let's start using gamma. And again, we're going to use this process. Remember? So now I'm going to divide by a T. Okay? And now I'm really seeing the fruits of labor of invoking ideal gas law. Okay? I just used the entry version of the first law combined with the second law for a reversible process to write this equation. Okay? Again, we're going to use enthalpy form of this. This is just definitions of enthalpy. So not too bad. Right? And I'm going to use the ideal gas law. Okay. So, right, getting from here to here uses ideal. Use ideal gas law. Perfect. Okay, so we have this expression right here. We're trying to derive isentropic processes, or that means we're reversible, where the ds is actually 0, where change in entropy is actually 0. That's where we're headed here. But let's use the CPs as well, right? So remember that CP, as we have there, that's going to be, right, a dH dt for ideal gas, right? So total derivative, it's just a number, so this equals just a number. Okay, that's P. And this is more important that CP is used a lot more than CV just because it involves enthalpy. And the gases are always a combination of the pressure work and the internal work. So you usually are going to the enthalpy expression instead of that volume expression. So DH, put the DH in there. Like that. This ideal gas law rewrite as Just use it. Just that last expression. You just use the ideal gas law to rewrite it with the ratios. Okay. Anything there? Yes. Okay, so put it all together. You now have this expression. Okay, and then if we integrate the entire expression, right, integrating lowercase d derivatives just end up being a great total change. So this is just, right, from any process, I go from entropy state 1 to entropy state 2. So little d's turn into like capital deltas. And then differentials here, Cp. You would still get a difference of here. Minus R. Right, and that's just the integration of, right, integrating 1 over p dp, you get this natural log relationship. You get a difference, and differences turns into ratios for logarithms. Right? So, for an ideal gas, we get this equation. This is true for any process. Right? Any process, as long as it's an ideal gas, obeys this relationship. I haven't said reversible or not yet because I haven't made this 0. Kind of another interesting thing you can do, right, is remember that R had a, right, remember that you can show that R is just the difference of the Cp and the Cv, right? So you can actually rewrite this in terms of just these gas properties. So whatever gas, any process that happens, it obeys this law. Now, I don't know if any of you would know these CPs or CVs values before, but do you see now, since this is a non-dimensional quantity and this is just natural log, that you now know what the units of entropy are even, just from this, right? This process relation says like, oh, all this time when you're looking up CP values and CV values, you're looking up units of entropy. So you can non-dimensionalize this actually, so, right, I'll just divide now by a CR because I'll get that gamma term if I do that. So this is, right, this is entropy scaled by the, right, scaled by the specific heat. Gamma, yeah, gamma. I've just taken the whole equation divided by a CP. So. And again, all this is going from state 2 to state 1 to state 2. So this is non-dimensional, right? Because I take an S divided by the Cp of the gas. So you go. So this is kind of interesting as well, right? Right. This number, right? The idea that there's something interesting happens if gamma were to equal 1, right? If it was actually the same, then, right, then this term would actually be gone. You only have a temperature-dependent property. Likewise, right, if it was 0, if it was like, right, if this ratio somehow this goes to 0, that means that CV is a lot bigger than CR. Then you would only get a pressure term. Can't happen though, right, because you don't have a negative R constant. So is that. You just kind of look at cases on actually the ratio, which one of these terms actually matters more, but they actually always be ordering 1. Okay, so before we do anything else, right, the whole point is for an isentropic process, now we say isentropic flow, because that says there's no change in entropy. So for an ideal gas law, for an ideal gas, you actually can only get this side of the equation using the ideal gas law. That's how you develop this right-hand side. The change in entropy is just going to be here no matter what. So you have to invoke isentropic to get this, to make this side 0. Isentropic, right, that means reversible. Right, it means a reversible process. It means it's done very slowly. It means you're not changing things too fast. You're just doing it really slowly so you can approximate. It's just like linking together steady states of a process. So that makes this thing 0. Okay, if that is 0, now this is 0, and you can now solve for different relationships of this based on the two states. And then you get the Gibbs equations, and I'll just write them out. And I think algebraically, extra credit, go ahead and do it, because it's fun. So state 2 and state 1, relating state 2 and state 1. And this is, okay, and then P2 for P1. Okay, these relationships come from using, again, the ideal gas law. You set those two things equal to each other, and then you can just go wild. Okay, so these are important. Gibbs equations. These relate two states of a compressible flow process, right? Any process, if it's isentropic, the two states are related this way. So, right, how many variables are in here? Well, there's 4 for each equation, right? So I have 1, 2, 3, 4. I mean, you have to assume that you actually know the gas. You could not, right? I mean, that's fine. So that's like there's then 5. So each one of these equations has 5 unknowns involved in it. That means you have to provide 4 to use them. You could use 2, maybe solve for 2 at the same time, but just get an idea of how you would actually have to use these things. Right? So you could use this to, like, if I don't know this, I need to provide 2 states, and you can figure out what gas it is. If you know what gas it is, you have to provide both pressures in one of the states. You can figure out the temperature at the end state of your process. Same thing with these densities, etc. But please don't use one of these equations if you at least haven't assigned 4 things to one of them. Okay. Same thing. You could use this one and this one, and there'd be 2 equations, and you have to set it up so you have 2 equations and 2 unknowns. Right. So you can know the gas. I'm just get a sense of how to use these things. They're just relating state 1 to state B of your compressible process. Okay, and those are the Gibbs equations. Those are used for all types of Those are used for all, like, you have a process and it's in state 1, and then you go to state 2. Okay, next is the speed of sound.